you for that. Want to get started here and really just want to provide, basically just give some motivation for what has been driving our thought process and our research, with ultimately the goal to generate basically mini livers that could either be used for modeling human liver disease, phenotype and function in vitro, with the ultimate goal to be able to transition these for use in vivo. And basically, one of the major challenges that has existed when people have wanted to work with hepatocytes or liver cells in vitro is that they rapidly de-differentiate, meaning that they rapidly lose their phenotype and function. And as a consequence, because it's been so difficult to maintain both the survival of liver cells as well as the phenotype and function of these cells in vitro, it really has created significant challenges to use and study hepatocytes in vitro. And, when we really think about this problem, then, this is really surprising, because if you guys know about the liver itself is a very unusual organ, such that when the hepatocyte, the parenchymal cell of the liver, is injured, basically either through toxins or drugs, the hepatocytes that are lost, the liver cells that are lost that die, are replaced rapidly through the proliferation of undamaged hepatocytes. However, when this process occurs too acutely in vivo or occurs chronically, it can lead to chronic liver diseases. And so, this is a huge problem in the United States, Europe, and throughout the world. Basically, over 20 million Americans and 29 million Europeans live with some form of liver disease. 3 million Americans and about 6 million Europeans live with the end-stage process of these liver injury processes. And as a consequence of that, 14,000 Americans are currently listed for liver transplantation. About 8,000 Americans and about 6,100 Europeans are transplanted each year. And as a consequence of this, about 31,000 Americans die each year from acute and chronic liver disease. It's the 12th leading cause of death in the United States. In Europe, about 85,000 Europeans die each year from acute and chronic cause of liver disease. It's the 5th leading cause of death overall in Europe. And worldwide, over 1 million people die yearly from cirrhosis. So if we were actually able to build a structure, a tissue that could actually maintain the differentiated function of liver cells, of hepatocytes, that prevented their rapid de-differentiation, maintain their function, maintain their survival, maintain their phenotype, you can imagine that these could be used in a variety of different applications, such that for both clinical practice and basic science. And more specifically, in the clinical arena, you can imagine that we could use these for drug testing, for the use in a bioartificial liver in vitro, or directly actually for transplantation as a construct in vivo. Now, in vitro, if we're able to maintain these cells long-term, maintain their function and phenotype, we can then use them as models to study both metabolic liver disease, hepatotropic disease processes, and also potentially as models to study both hepatocyte function and development. Now, when we think about the different components and the limitations that exist in hepatic tissue engineering, I've already kind of alluded to some of the major challenges in working with the cellular component of liver, the hepatocytes, that they rapidly de-differentiate. And the question is, what is the major driver for this process? And in a large body of literature that I'm not going to present today, basically what we and many others have shown is that the microenvironment, the environment in which these cells are sitting, actually dictate through both physical signals as well as chemical signals to the cells, and it's through these signals that help maintain the differentiated phenotype and function of hepatocytes. And so, if one were to drill down or go down more deeply, it's really these microenvironmental components that are really important in actually driving and maintaining hepatocyte function. And so it's actually, if you take these all together, the phenotype and function of the cells are actually going to be dictated by how we construct this environment. So basically, it's, as I've mentioned already, it's really important to try to include components of the hepatic or the liver microenvironment that would then mimic what we see in vivo, but now in vitro in a hydrogel. And many groups have tried a variety of different natural, non-synthetic approaches. And what was mentioned by Mitch, there's a lot of both variability and reproducibility issues with doing this. The other problem is the natural hydrogels, such as in Matrigel or collagen, don't readily recapitulate the elastic modulus or the stiffness that is what we find in vivo. And so basically, one of the advantages that attracted us to work using these peptide hydrogels was, one, that we can easily functionalize these gels with peptide motifs that are found in vivo in the liver, specifically RGD, and that this peptide can be easily incorporated into these hydrogels. Moreover, the stiffness of these hydrogels are actually quite similar to what is found in normal liver, as opposed to the variety of natural hydrogels, which actually the elastic modulus or the stiffness is significantly in orders of magnitude higher than what we find in vivo, and as a consequence contributes to some disrupted expression of a variety of different markers, as well as significantly impacts the function of the hepatocytes. So what I want to then show you here is we can then take gels that are made with or without this functionalized component, the RGD peptide motif. We can then rapidly make these gels with the hepatocytes embedded within them, and basically then show that these gels can maintain both their structure over time in vitro. And we're showing this here for 5 days, but we've actually been able to show that we can maintain their structure for several weeks. And this is just drilling down now, just microscopically here, using atomic force microscopy, showing that these peptide components, these motifs, are actually incorporated onto the surface of the hydrogel. And that when we then incorporate both hepatoma cells, so a liver-like cell line, HepG2, or primary human hepatocytes, we can actually produce both little spheroids from these. When we embed those spheroids within the hydrogel, incorporating this peptide motif, we can actually maintain both their structure here, and I will show you in a few slides their function. If we don't incorporate that, this is noted in the middle here, this peptide motif, we actually rapidly lose the differentiated, both the structure and differentiated function of the cells. That kind of makes sense, because what this is showing us is that the cells are actually able to interact with the hydrogel, and so they're actually both able to interact and sense what is going on around them. And as our controls, we use what is a standard system within the field, Matrigel, which actually has also a similar elastic modulus to the liver as well. But what we're going to show later on is, as opposed to Matrigel, we're not, then succumbing to some of the reproducibility issues that are often seen when using a natural hydrogel. So what we then looked was at using quantitative real-time PCR, was to see whether or not these peptide hydrogels are actually able to maintain the differentiated function of the cells. And so we looked at a variety of different domains of hepatic function by quantitative real-time PCR. We looked at a variety of transcription factors where we found they are more robustly expressed and maintained as compared to traditional two-dimensional model systems. We see that there's a significant improvement in expression of transporters and nuclear receptors, as well as a variety of cytochrome P450 enzymes. And these are markers or domains that are traditionally been very hard to maintain their differentiated function in vitro. And basically, these domains that we're looking at here are expressed at levels similar to what we see actually in vivo for primary human hepatocytes. And actually, all the data I'm showing you here is for primary human hepatocytes. So now, it's one thing to just show that on the RNA level that we're actually able to maintain the differentiated function of these cells, but these are actually functional activity assays run on these gels. And so what we find is that for several different cytochrome P450 assays, we actually are able to maintain the differentiated function of these cells at levels similar to that of the most robust 2D system that has been engineered. And we show that here for BFC, noted on the left, which looks at a variety of different cytochrome P450s. But then when we drill down and look at very specific, mature adult cytochrome P450s, such as CYP1A2, CYP2A6, and CYP3A4, we find that they're actually maintaining the cytochrome P450, a very mature marker of differentiated hepatocyte function, and one that's very, as I mentioned, very hard to maintain at levels very similar to that of what's seen in our very robust 2D system, and at levels similar to a gold standard in Matrigel. It's not just that they express these cytochrome P450s, but there's actually a lot of machinery within the liver cells that enable the liver cells to respond to a variety of toxins or other substrates or compounds in vitro or in vivo. And what we show is that when we dose these different compounds in vitro, such as omeprazole or rifampin, here noted on the left, we see an expected and appropriate level of induction of cytochrome P451A activity in vitro. When we look in a different assay, looking at CYP2A6, we similarly see a significant upregulation in the presence of omeprazole and rifampin. And one of the hardest challenges is maintaining CYP3A4 inducibility in vitro, and we see we can do that as well, both with, as denoted here with omeprazole or rifampin here for CYP3A4 induction. And you can see that the levels that we induce are actually even superior to the best model gold standard systems, both in 2D or 3D here, denoted here on the right here for rifampin and CYP3A4. So basically, if we were then to summarize what we've shown here, is first of all, that we can actually generate a synthetic peptide hydrogel that can create a 3D microenvironment that has a similar elastics modulus, similar to that of the native liver. And moreover, we can functionalize this hydrogel to incorporate binding motifs which enable cell-specific binding and cell-gel interactions, which is quite important. And basically, using these synthetic peptide hydrogels, we're actually able to maintain hepatocyte survival, phenotype, and function over time, and that we assess this with very specific and very challenging methods showing that they can maintain cytochrome P450 activity. And so, by doing that, we can now show that we can definitely model hepatocyte toxicity and injury and drug metabolism in vitro in a system that can maintain their differentiated function over time, and that in the future, our plan is to move forward and to use this to model more complex disease phenotypes